Right now, as you're watching this video, you are screaming through space at 67,000 miles per hour. Earth is hurtling around the sun faster than any bullet ever fired, faster than any spacecraft we've ever built. And here's what should terrify you. There's nothing holding us in place. No cosmic rope, no celestial track, no physical connection whatsoever. We are literally falling through empty space, and we have been for 4.5 billion years without ever hitting the ground. But here's the part that should really keep you up at night. Every physics calculation we've ever done says we should have been flung into the frozen darkness of deep space billions of years ago. The speed we're traveling at, the distance from the sun, the complete absence of anything connecting us. By all conventional logic, Earth should have drifted away into the cosmic void long before life ever began. Yet here we are. And nobody, not even our greatest physicists, can tell you with absolute certainty why the universe chose to keep us on this perfect merry-go-round instead of casting us into oblivion. What if I told you that the reason you're alive right now, the reason everything you've ever known exists, comes down to one of the most bizarre accidents in cosmic history? An accident so improbable, so perfectly calibrated, that if you changed it by even 1/10,000th of 1%, you wouldn't be here to watch this video. In fact, nothing would be here. No Earth, no life, no consciousness anywhere in our solar system. Before we dive into this mind-bending journey through space, time, and reality itself, smash that like button and subscribe, because what you're about to discover will fundamentally change how you see your place in the cosmos. And I'm curious, where in the world are you watching this from? And what time is it for you right now? Drop your country and local time in the comments. It's fascinating to think that people all over this orbiting planet are about to have their minds blown together. Let's begin. Let me start with a question that sounds simple, but isn't. What keeps the moon from falling on your head right now? Think about it. The moon is massive, about 81 quintillion tons of rock, and it's close enough that you can see it with your naked eye. Gravity is pulling it toward Earth constantly, every single second. So why hasn't it crashed into us? The answer most people give, because it's orbiting. But that's not an answer. That's just describing what we observe. That's like saying a plane flies because it's in the air. We need to dig deeper. We need to understand why orbits exist at all. Here's a better question. What if I told you the moon is falling toward Earth right now? Not metaphorically. Literally falling. It has been falling toward our planet for 4 billion years, and it will continue falling for billions more. The moon is in a constant state of free fall, just like an astronaut floating in the International Space Station, just like a skydiver before their parachute opens. Except the moon never hits the ground. Think of it like this. Imagine you're standing on a perfectly flat planet with no air resistance, and you throw a baseball horizontally. The ball travels forward, but gravity pulls it down, so it curves toward the ground and eventually lands. Now throw it twice as fast. It goes farther before landing. 3 times as fast, even farther. Now here's where it gets interesting. If you could throw that baseball fast enough, about 17,500 miles per hour for Earth, something magical would happen. The ball would still be falling due to gravity, still curving downward, but Earth's surface would be curving away beneath it at exactly the same rate. The ball would fall forever, continuously missing the ground, going all the way around the planet and coming back to hit you in the back of the head. That's an orbit. It's not floating. It's not levitating. It's falling with style. The person who first truly understood this was Isaac Newton, and the year was 1687 when he published it in his Principia Mathematica. But here's what most people don't know about Newton's revelation. He didn't just explain orbits. He unified heaven and earth in a way that got him accused of heresy by some religious authorities. Before Newton, people believed the heavens operated under completely different laws than Earth. The celestial realm was perfect, unchanging, divine. Earth was corrupt and temporary. They were separate domains with separate rules. Newton proved they were the same. The force that makes an apple fall from a tree in England is the exact same force that keeps the moon circling. Earth and Earth circling the sun. There was no distinction between terrestrial and celestial mechanics. One set of laws governed everything. This was philosophically revolutionary, almost as shocking as when Copernicus said Earth wasn't the center of the universe. But Newton's laws created an immediate problem that he couldn't solve, a problem that haunted him until his death in 1727. If gravity pulls everything together, why doesn't the entire universe collapse into one giant mass? Why are there separate planets at all? Why doesn't Earth just slam into the sun, or the sun into the center of the galaxy? His answer was essentially that God set everything in motion with such perfect precision that it all balanced out. The planets were thrown into their orbits at exactly the right speed and direction, and God periodically adjusted things to keep the cosmic clockwork running smoothly. Even Newton, the greatest scientific mind of his era, had to invoke divine intervention to explain why the solar system was stable. He was wrong about the God part, but he was right to be worried. The stability of orbits is far more precarious than most people realize. Let's get specific about Earth's orbit, because the numbers are going to blow your mind. Our planet is traveling around the sun at 67,000 miles per hour, which is 30 kilometers per second, or about 100 times faster than a passenger jet. At this very moment, in the time it takes you to read this sentence, you've traveled about 120 miles through space without feeling anything. The sun's gravitational pull on Earth is staggering. It's pulling us with a force of 3.5 times 1022 newtons. That's 35 followed by 21 zeros. To put that in perspective, that's roughly the force of 10 billion Tsar bombas, the most powerful nuclear weapon ever detonated, going off continuously every single second. That's how hard the sun is yanking on our planet right now. So why aren't we being pulled in? Because of something called orbital velocity. Earth is moving sideways fast enough that as the sun pulls us inward, we keep missing it. Imagine spinning a bucket of water over your head. The water doesn't fall out because it's moving fast enough that centrifugal force keeps it pressed against the bottom of the bucket. Earth is like that water, except instead of centrifugal force, it's our sideways velocity that keeps us from falling into the sun. But here's where it gets weird. If Earth were traveling just 5% slower, we'd gradually spiral into the sun. Our orbit would decay, and within a few 100 million years, we'd be consumed by solar fire. If we were traveling just 5% faster, we'd break free from the sun's gravity entirely and drift off into interstellar space, freezing into a dead ice ball within a few thousand years. 5%. That's the margin of error between life and death for every organism that has ever existed on this planet. Now you might be thinking, well, Earth obviously formed at the right speed, so what's the big deal? But that misses the deeper mystery. How did Earth end up at exactly the right speed in the first place? Was it luck? Was it inevitable? Or is there something about the formation of solar systems that naturally creates stable orbits? The answer involves a story of cosmic violence that would make every disaster movie ever made look like a children's cartoon. 4.5 billion years ago, our solar system was a churning disk of gas and dust orbiting a newly formed star. This disk, called the protoplanetary disk, was discovered and described in detail by astronomer Carl Sagan and his colleague in the 1970s, though the basic theory goes back to Immanuel Kant and Pierre-Simon Laplace in the 18th century. Within this disk, particles collided and stuck together through static electricity and weak gravitational attraction. Dust became pebbles. Pebbles became rocks. Rocks became mountains. Mountains became planetesimals, objects ranging from 1 kilometer to hundreds of kilometers across. And then the real violence began. These planetesimals smashed into each other at speeds of tens of thousands of miles per hour, Most collisions resulted in mutual destruction, both objects shattering into fragments. But occasionally, the angle and speed were just right, and two planetesimals would merge instead of explode. The bigger an object got, the stronger its gravity and the more material it attracted. This created a runaway process. Big things got bigger faster. But here's the critical part. During these billions of collisions, orbital energy was being exchanged. When two objects collided and merged, they created a new object with a new orbit, determined by the combined momentum of both original objects. It's like billiard balls on a cosmic scale. After countless quadrillions of collisions over tens of millions of years, the surviving planets ended up in relatively stable orbits, not because they were placed there, but because every other possible orbit resulted in objects either colliding with something else or being ejected from the solar system entirely. The planets you see today are the survivors, the lucky ones. For every planet we have, hundreds or thousands of protoplanets were destroyed or exiled into the darkness. Earth's orbit isn't divinely ordained. It's the orbit that didn't get us killed during the solar system's violent adolescence. But even that's not the full story, because Earth's orbit today isn't the same as Earth's orbit when it formed. In 1846, French mathematician Urbain Le Verrier noticed something strange about the orbit of Uranus. It wasn't moving quite the way Newton's laws predicted it should. The discrepancies were tiny, but they were real and measurable. Le Verrier hypothesized that there must be an eighth planet, beyond Uranus, whose gravity was tugging on Uranus and altering its orbit. Using only mathematics, only Newton's laws and a pen and paper, he calculated where this unknown planet should be. He sent his calculations to Johann Galle at the Berlin Observatory, and Galle found Neptune that very night, within 1 degree of Le Verrier's prediction. This was a triumph of Newtonian mechanics, proof that the laws discovered 150 years earlier could predict the existence of entire planets. But it also revealed something unsettling. Planets don't orbit in perfect isolation. They pull on each other. Every planet in the solar system is constantly tugging on every other planet, creating a fantastically complex gravitational dance. This is called the n-body problem, and it's the nightmare that keeps astrophysicists awake at night. For two bodies, like Earth and the Sun, the math is elegant and exact. You can predict their orbits billions of years into the future with perfect precision. But add a third body, like Jupiter, and suddenly there's no exact solution. The equations become what mathematicians call chaotic, meaning that tiny uncertainties in the initial conditions lead to wildly different outcomes over time. The terrifying implication is that we cannot predict with certainty where Earth will be in 100 million years. Not because our math is wrong or our measurements are imprecise, but because the solar system is fundamentally chaotic. Small gravitational tugs accumulate over millions of orbits, and eventually they can result in dramatic changes. In 1988, astronomer Jacques Lasker used powerful computers to run simulations of the solar system's long-term evolution. What he discovered was shocking. In some simulations, Mercury's orbit became so eccentric, so elliptical, that it crossed Venus's orbit, leading to a potential collision. In other simulations, Mercury was ejected from the solar system entirely. And in a handful of simulations, Mercury's destabilization caused a cascade effect that ultimately destabilized Earth's orbit. The probability was low, less than 1%, but it was non-zero. There is a real calculable chance that within the next few billion years, the gravitational interactions between planets could send Earth spiraling into the Sun or out into space. We are not as safely locked into our orbit as we thought. The solar system is stable on human timescales, even on civilization timescales. But on cosmic timescales, we're living on borrowed time. And here's what should really blow your mind. We got incredibly, impossibly lucky with Jupiter. Jupiter is by far the largest planet in our solar system, containing more mass than all the other planets, moons, asteroids, and comets combined. It's so massive that it doesn't actually orbit the Sun in the way you might think. Both Jupiter and the Sun orbit a common center of mass, called the barycenter, which is located just above the Sun's surface. Jupiter is so influential that it essentially controls the architecture of the entire solar system. And it saved our lives, probably several times. In the 1990s, astronomers began discovering planets around other stars, and what they found was baffling. Many of these exoplanets were Jupiter-sized worlds orbiting extremely close to their stars. Closer than Mercury is to our Sun. These hot Jupiters were completing orbits in just a few days, their atmospheres being boiled away by intense stellar radiation. Planets this large weren't supposed to form that close to stars. The theory was that they formed farther out, where temperatures were cool enough for ices and gases to condense, and then migrated inward over millions of years. This raised a terrifying question. Did Jupiter migrate? If so, where did it start? And why did it stop where it is now? Computer simulations by a team led by astronomers Cleomenes Siganes and Alessandro Morbidelli in 2005 proposed what's called the Grand Tack hypothesis. According to this model, Jupiter formed farther from the Sun than it is now, and as it interacted with the protoplanetary disk, it began spiraling inward toward the Sun. It was on track to become a hot Jupiter, which would have been catastrophic for Earth. As Jupiter migrated inward, its immense gravity would have scattered or destroyed any rocky planets forming in the inner solar system. Earth would never have existed. But something incredible happened. Saturn formed and began its own migration. When Saturn reached a specific orbital resonance with Jupiter, their gravitational interactions reversed Jupiter's migration. Both planets began moving outward again, settling into roughly the orbits they have today. This outward migration cleared out much of the remaining debris in the inner solar system, but it left behind just enough material for the rocky planets to form. If Jupiter had migrated a little faster, or if Saturn had formed a little later, or if the orbital resonance had been slightly different, Earth wouldn't exist. The margin of error was razor thin, but Jupiter's protection didn't end after the planets formed. To this day, Jupiter acts as a gravitational shield, protecting Earth from bombardment by comets and asteroids. When comet Shoemaker-Levy 9 broke apart and slammed into Jupiter in 1994, we witnessed this protection in action. Jupiter's gravity attracts or deflects objects that would otherwise potentially hit Earth. Without Jupiter, we'd be struck by extinction-level impacts far more frequently, probably too frequently for complex life to evolve. Think about this. You exist because a planet 500 million miles away happened to form at the right time, happened to migrate at the right speed, happened to interact with Saturn in exactly the right way, and continues to shield you from cosmic threats every single day. Your life is contingent on a series of astronomical coincidences that are so improbable, they verge on the miraculous. And we haven't even talked about the real reason orbits work yet. Everything I've told you so far is based on Newtonian gravity, the idea that massive objects exert an invisible force that pulls other objects toward them. For 250 years, this was considered absolute truth. Newton's laws explained everything from falling apples to the orbit of Neptune. But there was one tiny problem that nobody could solve. Mercury's orbit was wrong. Not dramatically wrong, but measurably wrong. Mercury's orbit isn't a perfect ellipse. It's more like a spirograph pattern, with the point of closest approach to the Sun, the perihelion, slowly rotating over time. This is called perihelion precession, and it happens to all planets due to their gravitational interactions. Astronomers could account for most of Mercury's precession using Newtonian mechanics and the influence of other planets. But there was a tiny discrepancy of 43 arcseconds per century that couldn't be explained. 43 arcseconds is incredibly small. It's like the width of a human hair viewed from 100 feet away. But science doesn't tolerate unexplained observations, no matter how small. Some astronomers proposed the existence of another planet, Vulcan, even closer to the Sun than Mercury, whose gravity could account for the discrepancy. Others suggested that Newton's law of gravity might need a slight modification at very close distances. The real answer was far more radical. In 1915, Albert Einstein published his general theory of relativity, and it changed everything we thought we knew about gravity, space, time, and reality itself. Einstein realized that gravity isn't a force at all. There's no invisible pull between objects. Instead, mass curves the fabric of space-time itself, and objects move along the straightest possible paths through this curved geometry. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and if you roll a marble near it, the marble will curve toward the bowling ball, not because the ball is pulling it, but because the marble is following the curved surface of the sheet. This is what planets are doing. The sun's mass curves space-time, creating what we visualize as a gravitational well, and planets move along geodesics, the straightest possible paths through curved space-time. From the planet's perspective, it's moving in a straight line. It's space itself that's curved. When Einstein applied his equations to Mercury's orbit, the 43 arcseconds of unexplained precession appeared naturally in the math. No hidden planet, no modification to gravity. Just the inevitable consequence of space-time curvature. This was the first major confirmation of general relativity, and it meant that everything Newton taught us about gravity, while extremely useful and accurate for most purposes, was fundamentally wrong about what gravity actually is. So let me blow your mind with this. Earth isn't orbiting the sun because the sun is pulling on it. Earth is traveling in a straight line through curved space-time. From Earth's frame of reference, there is no force acting on it at all. We're in free fall, just like astronauts on the ISS, just like a skydiver, except we're falling through four-dimensional space-time, curved by the sun's mass. And here's the really crazy part. Time itself is moving slower for you on Earth's surface than it is for someone in orbit. Gravity doesn't just curve space, it curves time. Clocks at sea level run slower than clocks on mountaintops. This isn't a tiny effect. It's large enough that GPS satellites have to correct for it. If we didn't account for general relativistic time dilation, GPS would be off by several kilometers within a day. You are literally experiencing time at a different rate than astronauts in orbit right now. Your subjective experience of time is being stretched by Earth's mass-curving spacetime around you. If this seems like I'm saying that gravity isn't real, you're halfway to understanding general relativity. Gravity, as Newton described it, as a force, doesn't exist. What we call gravitational attraction is actually just objects following straight paths through curved geometry, but the effects are real. You're still stuck to the ground. Planets still orbit stars. Black holes still crush matter into oblivion. The phenomenon is real. We were just completely wrong about what causes it. This raises a philosophical question that physicists still argue about. If gravity isn't a force, why does it feel like a force? When you're standing right now, you feel weight. You feel like Earth is pulling you down. But according to general relativity, you're not being pulled down. You're being pushed up. The ground beneath you is accelerating upward through space-time, preventing you from following your natural geodesic, which would be free fall toward Earth's center. Think of it like this. If you're in an elevator that's accelerating upward, you feel heavier. If the cable snaps and the elevator free falls, you feel weightless. But in both cases, you're in the same gravitational field. The difference is whether you're accelerating or in free fall. Einstein realized that there's no experiment you can perform inside a closed room to distinguish between gravitational acceleration and any other kind of acceleration. This is called the equivalence principle, and it's the foundation of general relativity. So when you feel weight, what you're actually feeling is the ground accelerating you upward, preventing you from free falling. Astronauts in orbit don't feel weight, not because there's no gravity in space. There's plenty. Earth's gravity at the ISS altitude is still about 90% as strong as on the surface, but because they're in continuous free fall, they're following their natural geodesic through spacetime without anything pushing on them. Now let's connect this back to orbits. Earth is in free fall around the Sun, following a geodesic through spacetime curved by the Sun's mass. We don't feel this because there's nothing pushing on us to prevent us from free falling. Everything, the planet, the atmosphere, you, your house, is falling together at the same rate. It's only when we resist free fall, like standing on the ground, that we feel weight. But here's what should keep you up at night. Einstein's equations predict that massive objects orbiting each other should create ripples in spacetime itself, called gravitational waves. As planets orbit, as stars circle each other, they create waves that propagate outward at the speed of light, carrying energy away from the system. This means that orbiting objects are constantly losing energy, and their orbits should gradually decay. For Earth and the Sun, this effect is so minuscule that it would take longer than the age of the universe for it to matter. But for extremely massive objects orbiting very close together, like two neutron stars or two black holes, gravitational wave radiation becomes significant. In fact, the first indirect evidence for gravitational waves came in 1974 when Russell Hulse and Joseph Tyler discovered a binary pulsar system whose orbit was decaying at exactly the rate predicted by general relativity. They won the Nobel Prize for this in 1993, and in 2015, the LIGO Observatory detected gravitational waves directly for the first time, confirming that Einstein was right and that these ripples in spacetime are real, measurable, and all around us right now. This means that orbits, even stable ones, are slowly spiraling. We're not in perfect circular paths that will last forever. We're on spirals that will eventually end, though for Earth, that end is incomprehensibly far in the future, but it will end. The universe will not allow perfect, eternal orbits. Everything eventually falls. Let's pause for a moment and consider just how bizarre the reality you're living in actually is. You are standing on a rock that's falling through warped space-time at 67,000 miles per hour. The only reason you're not falling toward the sun is that you're moving sideways fast enough to continuously miss it. The only reason you have a sideways velocity at all is because 4.5 billion years ago, countless planetesimals smashed into each other in just the right way to give Earth its current orbital energy. The only reason those collisions happened in a way that allowed Earth to survive is because Jupiter formed at the right time and migrated outward instead of inward. And the only reason Jupiter migrated outward is because Saturn reached a gravitational resonance with it at exactly the right moment. Your existence depends on a chain of cosmic accidents, so improbable that if you were designing a universe from scratch, you would never expect it to happen. And yet, here you are. But we still haven't answered the biggest question of all. Why does space-time curve in the first place? What is it about mass and energy that warps the geometry of the universe? Einstein's equations describe how it happens, but not why. They tell us that mass energy causes curvature, but they don't explain the mechanism. It's like being given a recipe that produces delicious cake without being told why flour, eggs, and sugar combine to create something entirely different from the ingredients. This is where physics gets uncomfortable. General relativity is one of the two fundamental theories of modern physics, the other being quantum mechanics, and they're incompatible. They describe reality in fundamentally contradictory ways. Quantum mechanics says that at the smallest scales, everything is discrete, quantized, probabilistic. Energy comes in packets. Particles exist in superpositions until observed. Uncertainty is fundamental to reality. General relativity says that space-time is smooth, continuous, deterministic. If you know the initial conditions precisely enough, you can predict the future with absolute certainty. These theories cannot both be completely correct, yet both have been confirmed by countless experiments to astounding precision. Quantum mechanics has been tested to 13 decimal places of accuracy. General relativity has been confirmed everywhere from GPS satellites to the gravitational waves from merging black holes. They're both right, and they both can't be right. The holy grail of physics is quantum gravity, a theory that unifies general relativity and quantum mechanics into a single framework. String theory is one attempt. Loop quantum gravity is another. But after decades of work by thousands of the smartest physicists alive, we still don't have a working theory of quantum gravity. And here's why this matters for orbits. At the heart of every massive object, at the center of every planet and star and black hole, space-time curvature becomes extreme. General relativity predicts that at a single point, curvature becomes infinite, creating what's called a singularity. But infinite quantities in physics are usually signs that your theory has broken down, that you're asking questions it can't answer. At the core of the Sun, which is curving space-time enough to hold Earth in orbit, quantum effects should become important. We can't describe what's really happening there with general relativity alone. We need quantum gravity, and we don't have it. This means that at a fundamental level, we don't fully understand why planets orbit. We have equations that work spectacularly well for all practical purposes, but we don't have a complete theory of the underlying reality. It's like watching a magic trick where you can predict exactly what the magician will do next, but you have no idea how they're actually doing it. We can predict planetary orbits centuries in advance, but we can't explain the deepest layer of reality that makes those orbits possible. Let me hit you with something that's going to sound like science fiction, but is absolutely real. There are objects in the universe that orbit so close to black holes, moving so fast, that time for them is measurably slower than time for us. There are stars orbiting the supermassive black hole at the center of our galaxy, Sagittarius A*, that complete an orbit in just 16 years, reaching speeds up to 2.5% the speed of light. At those speeds, time dilation is significant. Astronomer Andrea Ghez won the Nobel Prize in 2020 for tracking these stars over decades, providing some of the strongest evidence we have for the existence of supermassive black holes. And what she and her team observed is straight out of Einstein's predictions. The star's orbits precesses dramatically, not by 43 arcseconds per century like Mercury, but by degrees per orbit. Space is so warped near Sagittarius A*, that orbital mechanics become bizarre. Now imagine being on a planet orbiting close to a black hole. Your orbit would be insanely fast, space-time would be extremely curved, and time would be passing much slower for you than for someone farther away. This scenario was depicted in the movie Interstellar, where 1 hour on a planet near a black hole equaled 7 years farther away. The physics there was actually remarkably accurate, supervised by physicist Kip Thorne. This isn't fantasy. This is what general relativity predicts, and what we've confirmed with observations. Time is not universal, it's relative. Your rate of time depends on your motion and the curvature of space-time you're experiencing. And that curvature is what creates orbits. So here's the mind-bending revelation. Orbits don't just exist in space. They exist in space-time, a four-dimensional construct where time is woven together with the 3 dimensions of space. When Earth orbits the Sun, it's not just moving through space. It's tracing a helical path through space-time, spiraling forward through time as it loops around the Sun in space. If you could visualize all 4 dimensions at once, you'd see Earth's path not as a flat ellipse, but as a spiral through space-time. And because the Sun is moving through space as well, orbiting the center of the galaxy, that spiral is itself part of a larger spiral. And the Milky Way galaxy is moving through space, so add another layer. You're not just on a planet orbiting a star. You're on a planet spiraling through space-time, which is part of a star spiraling through space-time on a galactic scale, which is part of a galaxy moving through an expanding universe. There is no fixed point in the cosmos. There is no place that is truly stationary. Everything is in motion, orbiting, falling, spiraling through the curved geometry of space-time itself. If you're starting to feel small and insignificant, that's the wrong reaction. You should feel astonished that despite all this cosmic chaos, despite the incomprehensible violence of planetary formation, despite the precarious gravitational dance of the solar system, despite the fundamental incompleteness of our theories, you are here, conscious, aware, able to comprehend the mechanics of your own orbital motion through space-time. You are the universe experiencing itself. You are matter arranged in such a way that it can contemplate the warping of space-time and the nature of gravity. That's not insignificant. That's miraculous. We're about halfway through this journey, and it's time to address something that might be bothering you. If orbits are so precarious, if tiny changes in velocity or gravitational interactions can destabilize everything, how has Earth remained in a habitable orbit for billions of years? How has life had time to evolve? The answer is both comforting and disturbing. Earth's orbit is stable on billion-year timescales because of something called orbital resonance and tidal forces, which act as stabilizing mechanisms. But they only work within certain limits, and we're perilously close to those limits. Let's talk about the moon again, because the moon is slowly leaving us. Right now, the moon is receding from Earth at a rate of about 3.8 centimeters per year, roughly the same rate your fingernails grow. We know this because astronauts placed laser reflectors on the moon during the Apollo missions, and we can measure the distance precisely by bouncing laser beams off them. Why is the moon leaving? Tidal forces. The moon's gravity creates tides in Earth's oceans, pulling water toward the moon and creating bulges on both sides of the Earth. Because Earth rotates faster than the moon orbits, these tidal bulges are carried slightly ahead of the moon by Earth's rotation. The gravitational pull of these bulges tugs the moon forward in its orbit, giving it energy and causing it to spiral outward. Simultaneously, the moon's gravity pulls back on the bulges, slowing Earth's rotation. This is a beautiful example of conservation of angular momentum. The Earth-Moon system has a fixed amount of angular momentum, and it's being redistributed. Earth is spinning down, and the moon is speeding up and moving away. 4 billion years ago, the moon was much closer to Earth, perhaps only 15,000 miles away compared to 240,000 miles today. Days were only about 5 hours long because Earth was spinning faster. Tides were hundreds of feet high, catastrophically powerful. Over billions of years, the moon has moved outward, and Earth's rotation has slowed. Eventually, in about 50 billion years, if nothing else intervenes, Earth and the moon will become tidally locked to each other, with the same faces always pointed toward each other, and a day equaling a month, about 47 current days long. At that point, the moon will stop receding, because the tidal bulge will be directly aligned with the moon. But here's the disturbing part. As the moon moves away, its stabilizing influence on Earth's axial tilt decreases. Right now, Earth's rotational axis is tilted at about 23.5 degrees relative to our orbital plane, and this tilt is remarkably stable thanks to the moon's gravitational influence. This stability is crucial for life. The tilt is what gives us seasons, and the stability of the tilt over millions of years means that our climate has been relatively predictable. Mars doesn't have a large moon, and its axial tilt is chaotic. Over millions of years, Mars's tilt has varied from 13 degrees to 40 degrees. When the tilt is low, the poles are in permanent darkness and ice accumulates. When the tilt is high, the poles receive direct sunlight in summer, the ice vaporizes, and Mars experiences massive climate shifts. This chaos makes it nearly impossible for complex life to evolve on Mars. Earth almost certainly had a chaotic tilt before the moon formed. The leading theory for the moon's origin is the giant impact hypothesis, proposed by scientists William Hartmann and Donald Davis in 1975 and refined ever since. According to this theory, about 4.5 billion years ago, a Mars-sized protoplanet called Theia collided with the early Earth. The impact was so violent that it vaporized both Theia and much of Earth's crust. The debris coalesced into a ring around Earth, which eventually formed the Moon. This collision did more than create the Moon. It likely delivered the final portion of Earth's mass, contributed to our planet's iron core formation, and may have even delivered volatile compounds that later became our oceans and atmosphere. The Moon, born from catastrophe, became Earth's guardian, stabilizing our tilt and making complex life possible. But the Moon is leaving, slowly but inevitably. And when it's far enough away, hundreds of millions or billions of years from now, Earth's tilt will start to vary chaotically like Mars. Our stable climate will end, and any life that exists then will face environmental chaos. Before you start worrying about the Moon abandoning us, remember that the Sun has other plans. In about 5 billion years, the Sun will exhaust its hydrogen fuel and begin fusing helium. It will expand into a red giant, swelling to hundreds of times its current size. Current models suggest it will engulf Mercury and Venus, and possibly Earth as well. Even if Earth's orbit survives, the Sun's outer atmosphere will extend so far that our planet will be inside the star, experiencing drag that will cause our orbit to decay. Earth will spiral into the Sun and be vaporized. But here's something even more unsettling. The Sun is getting brighter. Right now, every 100 million years, the Sun's luminosity increases by about 1%. This is a consequence of hydrogen fusion, gradually changing the Sun's internal composition. As helium ash accumulates in the core contracts and heats up, increasing the fusion rate. In about 1 billion years, the Sun will be about 10% brighter than it is today. That might not sound like much, but it's enough to trigger a runaway greenhouse effect on Earth. The oceans will evaporate. The atmosphere will fill with water vapor, and Earth will become a hellish, uninhabitable world like Venus. All complex life will be extinct. The stable orbit that protected us for billions of years will become our tomb as the Sun slowly cooks us. And here's the really twisted part. Earth's orbit will barely change during this process. We'll still be at the same distance, still traveling at 67,000 miles per hour, still tracing the same elliptical path. The orbit that saved us will remain, but it won't matter because the Sun itself will have changed. The Goldilocks zone, the habitable region around a star where liquid water can exist, will shift outward. Earth will no longer be in it. This reveals something profound about orbits and habitability. It's not enough to have a stable orbit at the right distance. You also need a stable star, and no star is truly stable over billions of years. Every star evolves. Every habitable zone eventually becomes uninhabitable. In the long run, every orbit becomes a death sentence. Unless you move. In 2021, astronomers discovered an exoplanet called TOI2-109b, a hot Jupiter orbiting so close to its star that a year there is just 16 hours. It's spiraling inward due to tidal forces and will be consumed by its star within a few million years. This planet's orbit is decaying measurably fast, and there's nothing that can stop it. The laws of physics have condemned it. But here's what should blow your mind. If a sufficiently advanced civilization existed on that planet, or any planet with a decaying orbit, they could theoretically save themselves. How? By using gravitational assists, the same technique we use to send spacecraft to the outer planets. By repeatedly slinging spacecraft or asteroids past a planet in carefully calculated trajectories, you can transfer orbital energy, gradually moving the planet's orbit outward. It would require technology far beyond anything we have, machinery on a planetary scale, and thousands or millions of years of continuous effort. But the physics allows it. You could push a planet. Scientists have even proposed this for Earth, Before the sun becomes a red giant, a sufficiently advanced human civilization could use gravitational assists from asteroids to gradually spiral Earth outward, keeping us in the habitable zone as the sun evolves. Every 6,000 years, you'd need to swing a 100-kilometer-wide asteroid past Earth at just the right angle and distance. Do this repeatedly for 1 billion years, and you could push Earth from its current orbit out to Mars's orbit or beyond. It sounds insane, but it's theoretically possible. The orbit that formed by cosmic accident could be maintained by cosmic engineering. This raises a fascinating question. Could other civilizations be doing this right now? When we detect exoplanets in seemingly unusual orbits, could some of them be artificial, maintained by advanced aliens who refuse to accept the cosmic death sentence? We have no way of knowing, but it's a humbling thought. Your planet's orbit might be natural, but someday, if humanity survives long enough, it might be artificial. The difference between floating away and staying in place might eventually come down to choice rather than chance. Let me take you deeper into the strangeness of orbits by asking a question that seems simple. How many planets are in our solar system? You probably said 8, and you're technically correct by the current definition. But the real answer is, we have no idea. In 2016, astronomers Konstantin Batygin and Mike Brown published evidence suggesting the existence of a 9th planet, nicknamed Planet 9, lurking in the outer solar system. They haven't seen it directly, but they've observed that several distant objects beyond Neptune have orbits that are mysteriously aligned. The probability of this alignment happening by chance is less than 1 in 10,000. Something massive, perhaps 5 to 10 times Earth's mass, seems to be shepherding these objects into aligned orbits. If Planet 9 exists, it's orbiting somewhere between 400 and 800 astronomical units from the Sun. That's 400 to 800 times farther than Earth. Its orbital period would be 10,000 to 20,000 years. It's so far away and so faint that finding it is like searching for a black cat in a coal cellar. But the gravitational influence is there, warping the orbits of smaller objects in detectable ways. This is how we find planets now, not by seeing them, but by watching how they make other things move. We're using gravity as a flashlight, illuminating invisible mass by its influence on visible matter. And here's the disturbing implication. If a planet the size of Neptune can hide in our solar system, what else is out there? The Oort cloud, a spherical shell of icy objects surrounding our solar system, extends out to perhaps 100,000 astronomical units, halfway to the nearest star. We've never directly observed most of it. There could be dozens of undiscovered dwarf planets, perhaps even rogue planets, objects ejected from other star systems that were captured by the sun's gravity billions of years ago. Every one of these objects is in orbit, following its own path through the sun's gravitational well. Some orbits are stable for billions of years. Others are chaotic, intersecting with known planets, creating the possibility of catastrophic collisions. We're living in a shooting gallery, and we don't know where all the guns are. The most famous example is the asteroid that killed the dinosaurs 66 million years ago. It was probably about 10 kilometers wide, and it was in a perfectly stable orbit around the sun for billions of years until something, perhaps a collision or a gravitational interaction with Jupiter, nudged it onto a collision course with Earth. Orbital mechanics aren't just abstract physics. They're the reason you're a mammal instead of being ruled by dinosaurs. And it could happen again. We've identified about 90% of near-Earth asteroids larger than 1 kilometer, but we've only found about 30% of those larger than 140 meters. A 140-meter asteroid wouldn't cause a global extinction, but it would devastate a city or trigger a tsunami that could kill millions. And there are probably tens of thousands of them we haven't discovered yet. Every single one is in an orbit. Most orbits are stable and will never intersect Earth. But orbital mechanics are chaotic on long timescales. Given enough time, enough gravitational perturbations from planets, some of those orbits will change. Some will intersect Earth. It's not a question of if, but when. NASA and other space agencies are working on planetary defense, systems to detect potentially hazardous asteroids, and if necessary, deflect them. The DART mission in 2022 successfully demonstrated that we can change an asteroid's orbit by slamming a spacecraft into it. Humanity's first successful experiment in orbital engineering, and we did it to save ourselves from a threat that exists only because of orbits. The same mechanics that keep Earth safely circling the Sun also threaten us with extinction from rogue asteroids. Orbits giveth, and orbits taketh away. Now let's talk about something that's going to sound like I'm making it up, but I promise you, this is real physics confirmed by experiments. There is a point in space where you can park a satellite, and it will stay there indefinitely without using any fuel, as if frozen in mid-orbit. These are called Lagrange points, discovered by mathematician Joseph Louis Lagrange in 1772. In the Earth-Sun system, there are 5 Lagrange points, labeled L1 through L5. These are locations where the gravitational pull of Earth and the Sun, combined with the centrifugal effect of the orbital motion, create equilibrium points. Put a satellite at one of these points, and the forces balance out perfectly. The L1 point is between Earth and the Sun, about 1.5 million kilometers from Earth. The James Webb Space Telescope is stationed there right now. From L1, the telescope can observe deep space without Earth or the Moon blocking its view, and it can maintain a stable position relative to Earth using minimal fuel. L2 is on the opposite side of Earth from the Sun, also about 1.5 million kilometers away, and it's equally useful for astronomy. But L4 and L5 are where things get weird. These points form equilateral triangles with Earth and the Sun, 60 degrees ahead of and behind Earth in its orbit. They're gravitationally stable, meaning that objects placed there will naturally stay there even if perturbed slightly. And here's the mind-blowing part. They're not empty. Both L4 and L5 contain clouds of dust and potentially small asteroids that have been trapped there for millions of years. These are called Trojan asteroids when they're in Jupiter's L4 and L5 points, which contain thousands of known asteroids. Jupiter's gravitational dominance means these points are extremely stable. Earth's L4 and L5 points are less stable, but still trap material. We've even discovered at least one confirmed Trojan asteroid orbiting with Earth at the L4 point. Think about this. There are locations in space where gravity, which we usually think of as only pulling things together, creates stable parking spots. Points where the universe says, you can stop falling here. Science fiction writers have proposed building space colonies at Earth's L4 and L5 points, called O'Neill cylinders, after physicist Gerard O'Neill, who popularized the idea in the 1970s. These would be massive rotating habitats, kilometers long, providing artificial gravity through rotation. They could house millions of people in permanent orbit, not around Earth, but with Earth, locked to the same point in space as our planet orbits the Sun. And here's what will blow your mind. Those colonies wouldn't be in orbit in the traditional sense. They wouldn't be falling around anything. They'd be genuinely stationary relative to Earth, floating at a gravitational equilibrium point. It's almost like finding a ledge halfway down a cliff where you can rest without falling further. This reveals something profound about orbital mechanics. Orbits aren't just about objects falling around other objects. They're about navigating the complex gravitational topology of spacetime, finding the valleys and peaks and saddle points in the gravitational potential field. Lagrange points are saddle points, places where gravitational forces from multiple sources cancel in just the right way. But here's the catch. L4 and L5 are stable. L1, L2, and L3 are not. They're saddle points, balanced on a knife's edge. A satellite at L1 or L2 will drift away if not actively corrected. That's why the James Webb Space Telescope needs small thruster firings to maintain its position. It's not in a natural orbit. It's being held at an unstable equilibrium point by constant corrections. This is a metaphor for our entire situation. Earth's orbit is stable on short timescales, but chaotic on long timescales. We're balanced on a cosmic knife's edge, and staying here requires the universe to not perturb us too much. We're at the mercy of gravitational influences we don't control and can barely predict. But unlike the James Webb, we can't fire thrusters. We can't adjust our orbit. Not yet anyway. We're passengers on a planet following a trajectory determined 4.5 billion years ago. For now, all we can do is hope the knife's edge holds. Let's talk about what happens when orbits fail catastrophically. I mentioned the asteroid that killed the dinosaurs, but let me give you another example that's even more disturbing. About 4.1 to 3.8 billion years ago, during a period called the Late Heavy Bombardment, the inner solar system was subjected to an intense period of asteroid and comet impacts. We can see the evidence on the Moon, whose craters date from this era. What caused this bombardment? According to the NICE model, named after the city in France where it was developed, the orbital migration of the giant planets, particularly Jupiter and Saturn, destabilized the asteroid belt and the Kuiper belt, sending millions of objects on chaotic trajectories throughout the solar system. For tens of millions of years, Earth and the other inner planets were under constant bombardment. Impacts large enough to vaporize entire oceans happened repeatedly. If life existed on Earth before the late heavy bombardment, it was likely sterilized multiple times. The Earth we know today, the biosphere that eventually produced humans, arose after the bombardment ended. We exist only because the planets finally settled into stable orbits and stopped throwing rocks at us. But here's the terrifying part. We don't know if it's truly over. The asteroid belt still contains millions of objects. The Kuiper belt contains billions. If something were to destabilize them again, if a passing star perturbed the Oort cloud, if Planet 9 exists and its orbit evolves in a particular way, we could face another period of heavy bombardment. Orbital mechanics don't care about life. They don't care about civilization. They're indifferent equations playing out across billions of years. If the math says a rock will hit Earth, the rock will hit Earth. The universe is not trying to kill us, but it's also not trying to protect us. Now let me blow your mind with a different kind of orbital catastrophe. In about 4 billion years, the Andromeda Galaxy will collide with the Milky Way. When I say collide, I don't mean the stars will smash into each other. Space is so vast, and stars are so small relative to the distances between them, that actual stellar collisions will be rare. But the gravitational interactions will be catastrophic. As the two galaxies pass through each other, the orbits of hundreds of billions of stars will be disrupted. Some stars will be ejected from the merged galaxy entirely, flung out into intergalactic space where they'll drift alone for trillions of years. Other stars will have their orbits radically altered, sending them plunging toward the galactic center or spiraling outward. The Sun will likely survive, though our orbit around the galactic center will change completely. We might end up farther from the center or closer, or in a completely different part of the merged galaxy, called Milkomeda. Earth's orbit around the Sun probably won't be directly affected because stellar encounters will be so rare, but the night sky will be unrecognizable. The Andromeda Galaxy, currently a faint smudge, will loom overhead, filling the sky with billions of stars before the galaxies merge into a giant elliptical galaxy with no distinct spiral structure. If humans or our descendants still exist in 4 billion years, they'll witness the most spectacular astronomical event imaginable: galaxies colliding. And they'll know that the stable orbit around the galactic center that protected our solar system for 9 billion years is coming to an end. After the collision, the Sun might orbit the center of Milkomeda at a completely different radius, with a completely different period, in a completely different type of galaxy. Orbits aren't permanent. Not planetary orbits, not stellar orbits, not galactic orbits. Everything is temporary. Everything eventually falls, drifts away, or gets disrupted. The universe is in constant motion, and stability is a temporary illusion. We need to address the elephant in the room, or rather, the void in the room. Why is there so much empty space in the solar system? Earth orbits at 93 million miles from the Sun. Mars is at 142 million miles. That's a 49 million mile gap with almost nothing in it. Jupiter is 484 million miles out, leaving a 342 million mile void beyond Mars. Why are the planets so spread out? Why isn't there a smooth distribution of matter orbiting the Sun at every possible distance? The answer involves something called orbital resonance, and it's going to change how you think about empty space. Empty space isn't empty because there's nothing there. It's empty because anything that tried to be there got kicked out. When two orbiting objects have orbital periods that are simple ratios of each other, like 2 to 1 or 3 to 2, they're in orbital resonance. Every time the outer object completes 2 orbits, the inner object completes exactly 3 orbits, and they align in the same configuration. These repeated alignments create regular gravitational tugs that accumulate over time, either stabilizing or destabilizing orbits. The asteroid belt between Mars and Jupiter contains millions of asteroids, but it also contains gaps called Kirkwood gaps, discovered by astronomer Daniel Kirkwood in 1866. These are empty regions corresponding to orbital resonances with Jupiter. Any asteroid that forms or drifts into a Kirkwood gap gets repeatedly tugged by Jupiter at the same point in its orbit, gradually destabilizing it until it's ejected from the belt entirely. Jupiter has essentially cleaned out huge swaths of the solar system through orbital resonance. The empty space you see isn't naturally empty. It was swept clean by gravitational interactions over billions of years. The planets are spaced the way they are partly because those spacings avoid strong resonances that would destabilize them. But some resonances are stabilizing. Neptune and Pluto are in a 3 to 2 resonance. For every 3 orbits of Neptune, Pluto completes exactly 2. This resonance actually protects Pluto from colliding with Neptune, even though their orbits cross when viewed from above. They never get close because the resonance keeps them synchronized. This is mind-bending. Orbits aren't independent. They're interconnected through invisible gravitational couplings that span millions or billions of miles. Every planet influences every other planet. Every asteroid's orbit is shaped by interactions with Jupiter, Saturn, and the other giants. The solar system is a single, unified gravitational system, not a collection of independent objects. And it's playing music. When orbital periods form simple ratios, it's analogous to musical harmony. The solar system has a gravitational symphony, with planets and moons resonating at frequencies determined by their orbital periods. Some notes harmonize and create stability. Others clash and create chaos. The most beautiful example is Jupiter's moons. Io, Europa, and Ganymede, 3 of Jupiter's 4 largest moons, are in a 4 to 2 to 1 orbital resonance called the Laplace resonance. For every 1 orbit, Ganymede completes, Europa completes 2, and Io completes 4. They align in the same configuration, every Ganymede orbit, creating a gravitational dance that has remained stable for billions of years. This resonance has profound consequences. The repeated gravitational tugs from Europa and Ganymede stretch and squeeze Io, generating internal heat through tidal friction. This heat powers the most volcanically active body in the solar system. Io's surface is constantly being resurfaced by sulfur and silicate lava. The orbital resonance literally melts the moon from the inside. Europa experiences similar tidal heating, though less intense. This heating keeps Europa's subsurface ocean liquid, despite being far from the sun, where water should be frozen solid. That ocean might contain life. If it does, that life exists only because of orbital resonance. Life created by gravitational music. Think about what this means. The empty spaces between planets aren't empty because matter never formed there. They're empty because gravitational resonances swept them clean. And the matter that remains is arranged in a pattern determined by harmonic frequencies. The solar system isn't random, it's structured. It's organized by gravity into a pattern as intricate as any crystal or snowflake. You're living inside a gravitational instrument that's been playing for 4.5 billion years. Let's zoom out to the scale of the universe and confront the biggest mystery of all. Everything we've talked about, planetary orbits, stellar orbits, galactic orbits, all of it assumes that gravity is the dominant force on cosmic scales. But in 1933, astronomer Fritz Zwicky discovered something that shouldn't exist. He was studying the Coma Cluster, a group of over 1,000 galaxies bound together by gravity. By measuring how fast the galaxies were moving, he could calculate how much mass the cluster contained. But the answer was wrong. The galaxies were moving so fast that they should have escaped the cluster's gravity long ago. The cluster should have dispersed billions of years ago. Zwicky proposed that there must be invisible matter, which he called dark matter, providing additional gravity to hold the cluster together. Nobody believed him. It sounded absurd. Invisible matter? It was easier to assume he'd made a mistake. But in the 1970s, astronomer Vera Rubin studied the rotation curves of spiral galaxies and found the same problem. Stars in the outer regions of galaxies were orbiting far too fast. According to Newtonian gravity and general relativity, stars farther from the galactic center should orbit more slowly, just like how Neptune orbits more slowly than Earth. But Rubin found that stars at the edges of galaxies orbit at nearly the same speed as stars closer to the center. This should be impossible. Either the laws of gravity are wrong, or there's invisible matter creating additional gravitational pull. Decades of research have confirmed the latter. Galaxies are embedded in massive halos of dark matter, matter that doesn't emit or absorb light, doesn't interact with normal matter except through gravity, and comprises about 85% of all matter in the universe. Let me be clear about how disturbing this is. Everything you can see, every star, every planet, every galaxy, every atom in your body, represents only 15% of the matter in the universe. The other 85% is invisible and utterly mysterious. We know it exists only because of its gravitational influence on orbits. We've never detected a dark matter particle directly, despite decades of experiments. We don't know what it is, only that it must exist. Your orbit around the sun, the sun's orbit around the Milky Way's motion through space, all of it is dominated by dark matter. You are held in place by an invisible substance that science cannot explain. The very thing keeping you from floating away is the biggest mystery in physics. And it gets worse. In 1998, astronomers studying distant supernovae discovered that the universe's expansion is accelerating. This should be impossible. Gravity should slow the expansion, possibly reversing it into a big crunch. Instead, the universe is expanding faster and faster, as if something is pushing galaxies apart. This something is called dark energy, and it represents about 68% of all energy in the universe. Combined with dark matter at 27%, that means we understand only 5% of the universe. 5%. Everything we've ever observed with telescopes, everything we've ever studied in laboratories, every theory of physics describes only 5% of reality. The orbits we've been discussing, the gravitational mechanics that keep you alive, exist in a universe where 95% of the content is mysterious. We don't know what holds galaxies together. We don't know what's pushing the universe apart. We're like people watching a magic show, able to predict what the magician will do next, completely unable to explain how any of it works. This is the deepest answer to the question, Why do planets orbit instead of floating away? We don't fully know. Yes, we have equations. Yes, we can predict orbits with astounding accuracy. But the fundamental nature of gravity, the reason space-time curves, the identity of the dark matter holding it all together, and the nature of the dark energy accelerating cosmic expansion, all remain unknown. We live in a universe that keeps us in orbit through mechanisms we don't understand. And that should terrify and inspire you in equal measure. So where does this leave you? You've just spent 3 hours learning about orbital mechanics, gravitational physics, and the architecture of the cosmos. You've learned that you're falling through curved spacetime at 67,000 miles per hour. You've learned that your orbit is the result of countless cosmic accidents and gravitational resonances. You've learned that the stability you feel is temporary, that orbits decay, that nothing lasts forever. You might be feeling small, insignificant, a tiny speck on a tiny planet, orbiting an average star in a galaxy of 400 billion stars, in a universe of trillions of galaxies. What possible significance could you have in the face of such immensity? But here's what you need to understand. You are not separate from this cosmic dance. You are part of it. Every atom in your body was forged in the core of a star, dispersed into space when that star exploded, incorporated into the protoplanetary disk that formed the solar system, assembled into planets and organic molecules, and eventually arranged into you. You are literally made of stardust. That's not a metaphor. That's physics. And more than that, you are the universe becoming conscious of itself. For 13.8 billion years, matter has been clumping together under gravity, forming stars, planets, and galaxies. For most of that time, the universe was unconscious, just particles and fields obeying physical laws without awareness. But on at least one planet orbiting one star, matter arranged itself into structures complex enough to think, to question, to understand. You can contemplate the orbit you're on. You can understand the forces that keep you from floating away. You can predict the future and reconstruct the past. You can feel awe at the cosmic dance and dread at its indifference. You can ask why and actually discover answers. This is staggering. Out of the fundamental forces in particles, out of random quantum fluctuations, out of collapsing dust clouds and violent collisions, out of billions of years of chaos, emerged consciousness, emerged you. The universe spent billions of years preparing a stage for you to exist on. And now you have perhaps a century to look around, learn, love, create meaning, and then return to the cosmos. Your orbit, Earth's orbit, is a gift. Not from any deity, but from physics itself. The laws of nature, operating over incomprehensible timescales, created a pocket of stability in an otherwise violent universe. They created conditions where atoms could assemble into molecules, molecules into cells, cells into organisms, organisms into minds. And now you know how precarious it all is, how close we came to never existing, how many cosmic accidents had to align perfectly for you to be here. 5% faster orbital velocity, and Earth would have frozen. 5% slower, and we'd have burned. Jupiter forming a few million years earlier or later, and there's no Earth at all. The Moon forming from any impact other than the incredibly specific collision with Theia. And Earth's climate is chaotic. Life probably never evolves past bacteria. You won the cosmic lottery, but so did everyone else who's ever lived. Every human being is the beneficiary of the same impossible chain of coincidences. We're all children of this orbit, products of this perfect fall through curved space-time. And that means something. It means we're connected, not just to each other, but to everything. The carbon in your DNA, the calcium in your bones, the iron in your blood, all forged in stellar cores, scattered through supernova explosions, reassembled by gravity into planets, incorporated into life. You are a temporary pattern in the universe's matter, conscious for a brief moment before dispersing back into the cosmos. But while you're here, you're the universe's way of knowing itself. Every time you look up at the night sky and feel wonder, that's the universe marveling at its own existence through you. Every time you learn something new about physics or astronomy, that's matter understanding the laws that govern it. You're not insignificant, you're miraculous. And you're temporary, which makes you precious. Let me end with a prediction and a choice. The prediction: within the next few centuries, if humanity survives, we will likely detect life on another world. Maybe on Europa, protected by Jupiter's orbital resonance. Maybe on Enceladus, Saturn's moon with subsurface oceans. Maybe on an exoplanet orbiting a distant star. And when we find life, we'll discover that it too exists because of orbits. Because some planet or moon ended up at the right distance, with the right orbital stability, for long enough that chemistry could become biology. We'll learn that orbits are the cradles of life, the places where the universe's chaos momentarily abates enough for complexity to emerge. And we'll realize that we're not alone in our cosmic fall. Other worlds are out there, other intelligences perhaps, all held in place by the same gravitational mechanics, all temporary patterns in the cosmic dance. The choice: what will you do with this knowledge? You can't change Earth's orbit. You can't prevent the sun from eventually burning out. You can't stop the universe's expansion or solve the dark matter mystery. But you can choose how you live your century of consciousness. You can waste it, distracted and numb, never looking up, never wondering. Or you can live with the awareness that you're part of something immense and beautiful and utterly improbable. You can look at the night sky and see not just dots of light, but other worlds in their own orbits, other possible cradles of life. You can appreciate every sunrise as Earth completes another fraction of its orbital dance. You can feel gratitude for the cosmic accidents that made your existence possible. And you can act with the knowledge that we're all passengers on the same planet, held in the same precarious orbit, sharing the same brief window of cosmic stability. Our conflicts and divisions seem absurd when you zoom out to the scale of orbital mechanics. We're specks on a speck, orbiting a speck, in a galaxy of billions of specks, in a universe where 95% of the content is unknown. That perspective doesn't make life meaningless. It makes it more meaningful. Because if we're all this improbable, if our existence required this many coincidences, then maybe we should treat each other and our shared planet with more care. Maybe we should spend less time fighting over the temporary and more time marveling at the eternal patterns we're part of. The universe gave you an orbit. It gave you a century of consciousness on a stable world with liquid water, breathable air, and the mental capacity to understand your place in the cosmos. What you do with that gift is up to you. But whatever you do, remember this: you're not floating away. You're falling with purpose, tracing a path through curved space-time that began 4.5 billion years ago and will continue long after you're gone. You're part of the greatest dance in the universe, the orbital mechanics that structure everything from atoms to galaxies. And for a brief, shining moment, you get to know it. You get to understand it. You get to be part of the universe, waking up and looking at itself in wonder. That's why planets orbit instead of floating away. Not just because of gravity or curved spacetime or conservation of angular momentum, but because the universe needs places for consciousness to emerge, for matter to understand itself, for wonder to exist. You are the answer to the question. You are why orbits matter. Because without stable orbits, without this perfect cosmic dance, you wouldn't be here to ask why. Thank you for taking this journey with me. Thank you for spending 3.5 hours exploring the mechanics of our cosmic home. If this changed how you see your place in the universe, if it gave you a sense of wonder or connection or meaning, then hit that like button and subscribe, because there are so many more mysteries to explore together. And one more time, drop in the comments where you're watching from and what time it is for you right now. Let's create a snapshot of humanity around the globe, All of us orbiting together on this improbable rock, all of us briefly conscious, all of us falling through space-time together. Until next time, keep looking up, keep asking why, and remember, you're not floating away. You're exactly where the universe needed you to be.